the oxidation of alcohols with hypochlorous acid. So this is hypochlorous acid. And so we generate our hypochlorous acid in situ typically. So it's generated in situ. And we do this by mixing together sodium hypochlorite or bleach. You can actually use bleach from the grocery store for this reaction and it will do just fine. And we mix that with acetic acid, so CH3CO2H, and we usually do this at around 0 degrees Celsius. And this gives us hypochlorous acid. So these reaction conditions compared to the chromium reagents are really mild and a lot more environmentally friendly. So we're going to say this is mild and environmentally friendly. So if you can get away with using these conditions, it actually works really, really well in the laboratory and it's just a lot safer overall. And so what these conditions will do is it will do basically the same chemistry as you see with PCC, and that is, and I'm just going to write the HOCl over the arrow. We'll keep the temperature at 0 degrees Celsius. So what this will do is it will oxidize a primary alcohol to an aldehyde. So showing that same selectivity that PCC shows. So we can go from a primary alcohol to an aldehyde. Or if we had a secondary alcohol, it would oxidize that secondary alcohol to a ketone, right? And all of our oxidizing conditions do this. They all take a secondary alcohol and oxidize it to a ketone. We don't see selectivity there. There's only one option. What you always want to keep your eye on is what's happening to your primary alcohol, because a primary alcohol could be oxidized to an aldehyde, or if you're using that powerful chromic acid or Jones reagent, it could be oxidized to a ketone. So for this reaction, we're going to take a look at the mechanism. So let's draw the mechanism for this secondary alcohol that we have. So we've got an alcohol, right? And we have an acid. And so alcohols can act as bases, and we see this quite often. So it's going to act as a base and get protonated by our alcohol. And so we can do that. And now what we've done is we've made that alcohol into a good leaving group, and we've also generated a nucleophile here that can attack it. So we have that ClO minus, and this is going to displace the good leaving group that we just made. And so we've taken a good leaving group, and we're actually going to put another good leaving group on there. Okay. And then here's the step that does the oxidation. So when we're doing an oxidation, we've got to form a double bond here. So what happens at this point is you've got a hydrogen, and so you need to have a hydrogen atom on that alcohol carbon in order for it to be oxidized. And so this hydrogen can be removed by water. And this step here that we're going to show is essentially an E2 reaction concerted, where the water is going to take that proton, and here's where we form that pi bond, and we kick off the chloride as a leaving group. And so that's how this bleach oxidation works. And so we see that a primary alcohol can be oxidized to an aldehyde, a secondary alcohol can be oxidized to a ketone, and tertiary alcohols cannot be oxidized by these conditions or any of the other ones that we're going to see in this chapter. So we're only looking at the oxidation of primary alcohols and secondary alcohols.